All right, in the applications of exponential functions, typically for most of the problems, you're given information that allows you to put 2 points on a graph. I think what I said last time is that's the first thing you want to do. Okay, whether the video says do it or not, put 2 points on the graph. Okay, because then you have a basis for setting up a set of simultaneous equations you can solve for the parameters of the model. Now, we'll see what that means. You've got 2 points on the graph. Say, you take any 2 points. I mean, you put any 2 points on a graph. Now, if you're given an application, it'll tell you what the coordinates of these points are. This is what it comes down to, okay? Coordinates of the points. Now, if the coordinates are, let's say, 3, 6, and 10, 14. Okay, whatever the coordinates are. As we did last time, both in this class and the 161, you got 2 points. You make a sketch of an exponential curve. This gives you something to focus on rather than just get lost in a bunch of values. Okay. Now, you have questions. Go to this graph and answer some of the questions. The question is, what's the value of y when x is, whatever y is, when x, whatever that is let's say 5. Okay, you can make an answer. If this is 3 and this is 10, and if you've got a reasonably well-scaled graph, you come out where 5 is here, you go up, you come over, and you can estimate what the value would be. Okay, and this keeps you honest. If you can draw the graph, even if it's not a particularly accurate one, if you can draw the graph, you can make estimates and then check your work by seeing if your estimates actually make sense in terms of the graph. Okay, in terms of make sure your results make sense in terms of the graph. We're going to get a function. We can plug 5 into the function and see what the value should be. Okay. And we did that last time. If you want to find the doubling time, right here's a value. The value doubles, it's going to take this about this long, and that looks like it maybe takes 5 or 6 units to double. So review what we did as far as the graph, because it gives you a picture. It gets you oriented to what the algebra is going to tell you. Okay. So anyhow, we graphed the 2 points, and then of the coordinates of each point into the form, which could be y equals a, b, the x, or y equals a times 2 to the x, not 2 to the kx, or y equals a times e to the kx. Any one of these forms will give you a valid exponential function, and you can change from one form to the other. Now, this form and this form are the ones you're going to see most often. This form can be handy because you have a doubling time was built into that function, so it can be convenient, but it's usually going to be this one or this, especially if open math is asking you for the formula. All right. So let's just take these 2 points and plug them in. Let me just ask you, take these 2 points and plug each point into the function to give you a pair of simultaneous equations. And let's use this form, because we kind of emphasize this form last. Please go ahead and do that. Let's see what you get. And gee, doggone it. This thing decided to just zoom itself back to Boone, North Carolina. I don't need to do this with the camera. Just reiterating what I said, I don't know why the camera decided to do what it did, but it did. We're applying exponential functions, given 2 points, let's find the function. Okay, well, here's a picture. We've got 2 points. And you saw me do this, but you were, miles away last time you saw it. This is what I was doing. I don't know if you could see it all that well. So if we put 2 points on. Now, how do we get 2 points from the information? Well, we'll take a look at that, but I don't want to get into a complete detail here. So all the details of how we get 2 points. We talked about that last time. You can review that, and we might be able to talk about it this time, but there's some other stuff we need to do too. Okay, so anyhow, here's 2 points. So we sketch what looks like an exponential curve. You should be adept at sketching these curves, although if you give it 2 points, it can be kind of hard to figure out how to put them. But draw a reasonable curve so you can make estimates to check the results of your work. Okay, so we graph the 2 points, then we plug the coordinates of each point into one of these 3 forms. And I know you couldn't see the form when you got y equals ab to the x, or y equals a times e to the kx, or even y equals a times 2 to the kx. Each of these has its advantages. We're going to choose this one, the a e to the kx. So what you're doing, while I go back over what I said, is show me what your 2 equations are when you plug those points in. Okay, so I'm convinced that once you get 2 points in the graph, you can write these equations out. Everybody did that correct. And the 2 points we have here, okay, the form. The point 3,6 gives you, that's an arrow, not an equal sign. I'll write that as 3k, even though it says kx. Kx is the same as x times k, and x is going to be a number. We usually want to put the number out in front, but we can't actually confuse ourselves if we don't do that. If you don't confuse yourself, do it anyway. It works. But if you're not sure, it's the way I do it. Okay, so here are 2 equations. How do we solve these 2 equations? Well, we went through that in detail last time. We're going to go through it a little more quickly with the green arrows. I used green arrows last time. Okay. Take the first equation. And we solve it for a. Well, the solution is A equals 6/e⁻3k. Now I'm skipping the steps where we divide both sides by 3k. You need to write that step out to reinforce it because people are still confusing how you get rid of that 3k. Okay, some people want to subtract it. Okay, I've seen a worrisome amount of that. This is a multiplication. You don't undo a multiplication by subtracting. Anyhow, we get this. Okay, so we take this and we plug it in here, which gives us 14 equals a e to the 10k, but we've seen that a could be written as 6/3k, so we do 6/3k instead of a. And it's not over 3k, it's over e to the 3k. Times e to the 10k. Now we've got an e to the 10k divided by an e to the 3k. By the rules for exponents, you're going to subtract the exponents. So this gives you 14 equals 6 e to the 10k minus 3k, or 14 equals 6 e to the 7k. Now we can solve for k. Look at what we've done. We took the first equation and we solved it for a. We plugged that expression for a into the second equation, and now we don't have an a anymore. We can't solve either of these equations by itself because there are two unknowns. One equation with two unknowns can have an infinite number of solutions for those two unknowns. You've got to get one solution. So we eliminate a with this step and this step. So we've eliminated a and we've got an equation only for k, and now we solve this equation. Okay, so we solve for k. First of all, we put this into the form of a base to a power equals number or quantity. And we get this e to the 7k equals 14/6. And just to simplify things a little bit, we can reduce 14/6 to 7/3. Now, if e to the 7k equals 4/3, then the log base e of 4/3 equals 7k. And now we can find k. It's going to be the log base e of 4/3 divided by 7. Now, log base e is just the natural log, and that's convenient because you have a natural log key in your calculator. So let me write this first of all. Right, this is natural log of 4/3 equals 7k. Because log base e is the natural log. And then k is going to be the natural log of 4/3 divided by 7. And you can punch that into your calculator. Now, let's see, what is the natural log of 4/3? Well, you need your calculator to do it. I think it's 7. It's going to be negative. You know, Somebody's trying to tell me something and knows enough not to talk while the camera's on. Okay, well, I'm glad somebody got my attention there. Somehow I had 7/3 here and then I had 4/3 here. And I like 7/3 a lot better because that's easier to, it's easier to estimate the natural log of 7/3 than it is to estimate the natural log of 4/3. So for two reasons, one for the sake of accuracy, and the other for the sake of not straining my ability to estimate any more than necessary. And the reason this is really pretty convenient is 7/3 is 2.33 and E is 2.71. Okay. So 7/3 is pretty close to E. So I know that the natural log of E is 1. Natural log of number less than E is between 0 and 1. Okay. And trying to visualize, here's E, here's 2.7. I'm going to say it's about by that. I think I'm gonna get something like maybe 0.11. Okay. Well, that might be right, but I don't think 0.11 doubling time we're at 6. We kind of be between 6 and 7. So I can cheat with the doubling time on this graph, but you can kind of remember that this is what I'm doing in my head. 0.11, maybe 0.12. Okay, now you punch it in your calculator and get the right answer, but we've got a value of K. And it's more or less not too far from being accurate. And more or less a little bit too far from what I'm looking for. Oh, there it is. Hang on. This out. Okay. Now let's continue. Okay, K is 0.11. Now we need to evaluate A to complete this model. We need a number for A and we need a number for K. We've got a number, an approximate number for K. If you use your calculator, you'll get an even better number. Okay. This one isn't bad, but please don't think that that's totally accurate. So and yeah, what I'm writing is correct. Okay. Pick one of these equations. Okay, pick the first one. This equation comes from here. 6 equals A e to the 3K, so 6 equals A e to the 3 times 0.11. 6 equals A e to the 0.33. Now I have two choices as usual. I can either stand up here, reach for calculator, punch numbers in. I can use my head, try to estimate e to the 0.33. I can visualize the graph. E to the 0 is 1. E to the 1 is 2.7. E to the 0.33 is over here. So I can't do a real good estimate of that actually using Taylor series. That's kind of a big number. I'm gonna say that e to the 0.33 is about 1.4. Okay. Probably around 1.4, 1.5, 1.4, maybe even just 1.3. Anyhow, there it is. The 6 equals a times whatever we get when we do e to the 0.33. Then a should be approximately equal to, and all these are approximate, okay? Because the 0.11 is very approximate. Okay. So we solve for a, it's going to be 6 over 1.4. Okay, that's about 4. So A is 4.3, K is 0.11 approximately. And our model is y equals AE to KX, which we can now write as y is approximately 4.3 times e to the 0.11x. And that's really not anywhere near what the graph would predict. Well, actually it is. Okay. So, you know, here on this line, y equals 6. Go halfway to the origin, and here's y equals 3. Well, this looks more like 4 than 4.3. Maybe it's not even 4, but it's reasonably close to 4.3. Could this be y equals 4.3? Looks a little low, but first place, it's a freehand graph. We don't expect it to be completely accurate. Okay. Second place, you know, there are a bunch of estimates involved. It's plausible. Plausible if this graph just had a slightly different shape, we'd have 4.3 there. Now remember, the 4.3 here is something I estimated numerically in my head. With the aid of a mental picture of the graph and also with a Taylor expansion that you don't know anything about and probably would never have a need to, okay? It's a second semester calculus topic. So my point is that you do this with your calculator, you're going to get a much more accurate model. But if you did a half decent job on your graph, make sure you have a reasonable scale and so forth, and you compare what y should be when x equals 0. Now, what I say, I wish I'd have that y equals 4.3 here, because x equals 0. And if x equals 0, we have e to the 0, which is 1, and y would be 4.3. That's always going to be the case on any of these models. If x is 0, you're going to get y equals a, right? Okay, so whatever a comes out when you do all this stuff, that's going to give you the y-intercept. We can also estimate the doubling time by the rule of 72, rule of 70, whichever rule you happen to be using. 11 goes into 70 about 6.5 times. And this tells us that the doubling time ought to be about 6.5. So if we start here, if this is 3, 6.5 to be out about here. We double when we get to this point. There's 4.3 and another 4. It looks like it pretty much doubles. Now you have to know how to see a doubling time on a graph. I'm not going to re-explain that. Some people are going to be better at estimating that than others, but it's very beneficial if you can estimate it. And again, let's just review what we did. First of all, you got an application problem. Of course, the application problem requires that you be able to estimate 2 points in the graph. It really requires that you be able to write these two equations. I'm strongly advocating that you do this by putting 2 points in a graph and sketching an exponential shape based on those 2 points, and that you do a reasonably careful model, a careful job of scaling your graph consistently. Then, just looking at those 2 points, you can write the equations. Everybody wrote the equations. Once you have the 2 points, you can write the equation. Now, can you go through the algebra steps of doing this? It's a little bit challenging, okay? We've got a couple of extensive examples from the video from last time. You have the videos from Open Math that show you the same process, maybe in a manner that has details that you like better than what you see here, and that's fine, okay? But that's the process. People had trouble with this assignment, which is not unusual. This is where you apply an exponential function, the whole idea of exponential functions to the real world. This is what the course is all about for most people, unless you're going to be a mathematician or physicist, okay? And if you're going to be a mathematician or physicist, and we have had people, well, most people are going to be mathematicians or physicists have already had math well beyond this course. We did have one student a few years ago who started this course with the ambition of becoming a PhD mathematician. And he came to me in the hall one day. He wasn't in my course. I was just teaching all the upper level courses at that time. Said he was going to be in my physics and calc and wanted to do my linear algebra class while he was taking his first calculus class. And I thought, okay, you know, I'm not going to tell the guy your chances of becoming a PhD mathematician starting at a community college in free calculus are pretty minimal. Okay, turns out the guy was brilliant. He did all kinds of stuff. It just blew me away. It was great working with him. And he absolutely had not just PhD aptitude and work habits, but he would have been a PhD with distinction. Then he decided to go into psychology. Well, I mean, he's doing it. He's at a top-notch school and is just finishing up the second year of graduate school. Haven't seen him since last summer, so I hope I'll see him at least get an update on what he's doing, because he's also taken the advanced math courses. And with the idea of doing heavy-duty statistics, research, and really understanding how the brain works. Okay. Anyhow, that's a digression. My point really is that, you know, over 50 years of teaching here, I've had a handful, maybe close to 2 handfuls of students with that ability. Okay. And yeah, that's great. And those people do occasionally appear in free calculus course. Almost of them did. Much of them were higher courses. So my comment that almost nobody in pre-calculus is going to go much beyond the ability to model things in the real world, okay, and use that in their profession. As a result, to say that this is really one of the big focuses of this course. I just want to kind of emphasize that in that long digression is irrelevant, just disregarded. Although remember that there are people out there who are so smart that it's ordinary mortals don't understand what the heck. Okay. Okay. Here we have two linear equations, and we're going to try to find a value of x and a value of y that satisfies both of them. Okay, so some pair x and y. If we plug in here, we're going to get 16. If we plug in here, we're going to get 6. First thing we want to do is we want to sketch a graph where we have this equation on one, the graph of this equation and the graph of this equation. Now, both of these equations are linear. They both give us straight lines. So the question we're going to discuss for a minute is how do we go about graphing these two equations? Now, if you need to review how to graph straight lines, you should review that like right away. Because you're going to have to draw some straight lines to do these assignments. I'm just going to comment. Okay, x-intercept this equation refers when y equals 0. Y equals 0, 8y is 0. That gives us 2x equals 16. Divide both sides by 2, we get x equals 8. So the point 0, 8 is on the first graph. And if we let x equal 0, we're going to get the y-intercept. Well, if x is 0, then we get 8y equals 16. And we get the point 0, 2. And I labeled my point over here wrong. Doing this stuff for 100 years. And I still want to reverse. And I want to write my coordinates down in the order in which I found them, rather than the order in which they should be written down. So that should have been 8, 0. Okay, so well, there's 2 points. There's my straight line. Now I'll label this line 2x plus 8y equals 16. I do the same thing for the second graph. If y is 0, x is going to equal 3 halves. Negative, yeah, 3 halves. So let's see if that's 2, here's 1, and here's 3 halves. And if x equals 0, I get negative 2y equals 6, y equals negative 3. So that might be about here. And now my graph for this function looks like this. I label it 4x minus 2y equals 6. And I've got a picture that I try to estimate the coordinates of this point. Well, it should be clear that the y coordinate of this point is just a little less than 2. So if 1 is here and 2 is here, I'm going to estimate that y coordinate. the, I'll say 1.8 y coordinate, and the x coordinate would be like here. If this is 8, and here's 4, and here's 2. I'm getting something very close to 1. Well, my conclusion is that we should nearly satisfy both equations. So x is 1, y is 1.8. We plug that in. If x is 1, 2x is 2. 1.8 times 8 is 14.4. Okay, 14.4 and 2 is 16.4. So if we plug in x equals 1 and y equals 1.8 into the first equation, we get something very close to 16 on this side. We don't expect that we come out exactly right because this is a hand sketch graph, by darn, and we've got a lot of estimates. We've got to be careful to do a decent job of scaling the graph. Otherwise, our estimates aren't going to be worth anything. Okay? Or at least it won't be worth much. Now, I don't know how we're going to do satisfying this, but let's see. Wait a minute. Well, that's not going to work at all. The second equation, what's wrong? I think something really stupid here. Certainly wouldn't be. Yeah, I did. It looks like I should have had 3 halves 0 and 0 -3 on my graph. So I just totally blew it. Okay. So I got coordinates that worked pretty well here. I pretended to reverse these coordinates. I didn't really pretend, I really did it. And then when I tried to check the second equation, I got something that didn't make any sense. First equation looked pretty good. If I plug these coordinates in, I get something really close to 16. So I'm thinking, yeah, I did a good job. Okay, well, now what? This should have been 3 halves 0. This should have been 0 -3. And my graph should have been like here. Okay, it should have been much steeper. So I was not very careful. And as I said, I have a penchant for reversing my coordinates, but I don't always think about it. So even though I commented here, I went ahead and did it on both of these points. Having done it in the first, it was very natural to do it in the second. So that was a bonehead thing. And my point is that leads me to a bad conclusion. If x equals 1 and y equals 1.8, well, if x is 1, I get 4 here. If y is 1.8, I get -3.6 here, which gives me 0.4, and 0.4 is nowhere near 6. So gives us this on the first equation, okay? Just plugging it in, doing the arithmetic, I get 16.4 equals 16. This is close. So far, so good. Now check the second equation. We plug in 1 for X, plug in 1.8 for Y, and we get 0.4 equals 6. Okay, that's a disaster. What happened? Well, what happened is well, I don't have room to write. I should, intercept should have been, instead of 0.3 halves. On the second equation, the intercept should have been -3 halves 0. And 0, -3. Should have been, sorry, 3 halves 0 and -0.3. So this equation, it's a perfectly good graph, but it's not this. So I'm just going to kind of obliterate that graph. That could erase it, but it would mess up a lot of things even more than I messed up. Correcting that error, I see that I should have had three halves 0, which would be about here, and 0, -3, which should have been down about here. So now, when I redraw the straight line, this is the correct line. The second equation. And right here is my point of intersection. And it looks like the coordinates at this point are about, looks like 2.5 and 1.5 maybe. Okay. So if I make my estimates, get 2.5, 1.5, and if I plug those numbers in, 2.5 times 2 is 5. 1.5 times 8 is 12. I get 5 plus 12 equals 17. That would give me 17 equals 16. That's pretty close. So it means that my estimate isn't bad. Now let's see if my log pulls out. 2.5 times 4 is 10. 2 times 1.5 is 3. 10 minus 3 is 7. So I get 7 on this side, 6 on this side. That's pretty close. Okay, so I can say now Let's say these values check out nicely, though not perfectly. I get 17 equals 16, I get 7 equals 6. If both these values are a little bit less, could be closer. But maybe one needs to be a little bit more or less, one needs to be a little bit bigger, doesn't matter. We've got a pretty good idea what the solution ought to be. Okay, now I didn't intend to illustrate the potential flaws quite that dramatically. Okay, reversing the coordinates here gave me something that just turned out to be really bad. Okay. Worked out well for the first equation, didn't work for the second. At that point, I had to stop and look something. Okay. I learned that if I reverse my coordinates, it doesn't work. Well, I knew that already. But I identified my error, which I could then pretty easily correct and get a good estimate. Okay, well, estimates are just estimates. Now, you know, what we did earlier with estimates on the exponential graph, those estimates aren't completely accurate, but they give us some guidelines. They give us an idea whether our algebra is correct or not. Okay, my estimate there gave me the idea that my algebra, well, I didn't have the algebra, I'm estimating I had a flaw, but we fixed it. And now we know pretty much close to what we ought to get. Okay, well, let's do the algebra now. Okay, the algebra, we have the equation. This one. Okay. Now I observe. If I multiply this second equation through by 4, in other words, multiply the left-hand side by 4 and the right-hand side by 4, the equation is still true. Totally equivalent to the equation I got. If I was to graph that equation, I would come out with exactly the same intercepts and exactly the same mark. So if I multiply this equation by 4, I have an equivalent system. Well, let's do that. Now I'm going to use a notation here. I'm going to call this equation 1 is this equation, okay? That equation is 2x plus 8y equals 16. And then I do 4 times the second equation. Gives me 16x minus 8y equals 24. Okay, understand what I've done. Might not understand why I did it, but do you understand what I've done? Do you understand my notation? Make sure. Okay, now I don't, as usual, people don't necessarily understand everything I did. Let's make sure we understand what I've done. Okay, I've write down the second equation again, with the second equation multiplied by 4. If you graph this equation, really need more words for that, but I've got the idea, like, was to graph this equation, well, let's think about it. What are the intercepts? If x is 0, I get -8y equals 24, right? Solution is y equals -3, so I got the point 0, -3. Right there, same as it was before. And let me pull this over a little further. See that point, I'm sorry. I really need to improve this setup a little bit so I can see what I'm doing. Okay, so now I can see the screen and I can see that I can see it. Okay. So there's my point 0, -3. It's the same y-intercept that I would have gotten up here because everything's just been multiplied by 4. 24 is 4 times 6. -8 is 4 times 2. So when I divide 24 by -8, I get the same thing I did when I divided 6 by -2. Find my x-intercept. Well, it's still going to be, we're going to get 16x equals 24. We're still going to get x equals 3/2. We're going to get the same x-intercept. We're going to get exactly the same blue line. We're going to have exactly the same picture. And it's important to understand that. At least it's very useful to understand that. Now, yeah, I can still see what I've got here. Okay. So it's important to understand what I've said here. So we understand what we're doing. This system is totally equivalent to this system. Okay. Now, this equals this, and then we've got to wait until you start writing, so we'll have, because you got to watch what I'm doing. Okay, so actually, please don't take time to copy all these words down. Listen to what I said, try to understand it. If you don't, take yourself a note, go back to it. Okay. Probably 35, 40 minutes into the video. I don't know, I've been talking a lot, but it's longer. Okay. Now, watch carefully. This is equal to this, right? Okay. And this is equal to this. So if I add this and this, it's got to be equal to whatever I get when I add this and this. Okay. This plus this has to equal this plus this, because this equals this and this equals this. If I add these things together, what do I get? Write down what I get if I add the left-hand sides. What do I get if I add the right-hand sides? Okay. No, that's pretty good. Okay. So we see that if we add these two, well, we're going to get 40. That's the easy part. Okay. Over here, we got to add this to this. Well, 2x and 16x makes 18x, so we're certainly going to get 18x. And 8y minus 8y is 0. Well, look at what we've done. We eliminated y, and we can solve for x. And then we do that a little while ago with the two simultaneous equations for the exponential function. Yeah. Okay. Let me say also, this was done back in chapter 2. There are parts of the assignment that did all this, so you might want to review that because everybody I think did the assignment. Okay, well, so we got 18x equals 40. So that x is 40 over 18, which is 2 2/9. Okay. And that's approximately 2.22. I did that right. Yeah, that's right. Now, let's go back to our estimate for the x coordinate when these things cross. We got 2.5, 2.5. Okay. Compare with Okay. Compare x equals 2.2 with the graph estimate, which was x equals 2.5. What did we get? Well, I mean, what we get is we're pretty close to the graph estimate. Now, remember, the graph estimate didn't give us an exact match for the first equation. It gave us 17 equals 16. Second equation, our graph estimate gave us 7 equals 6. It's close to being right, but it's not totally right. So we found the exact value, which is this. The decimal approximation I just wrote down so we can compare it with the decimal approximation we made on the graph. Okay. How do we know that x is 2.2? Sorry, that x is 2 and 2/9, which is really 20/9. So reducing 40 over 18, we get 20/9. We take this. And we'll plug it into the second equation. That's going to give us 4 times 20/9 minus 2y equals 6. And we can solve this for y, and then we'll have the exact y coordinate where those lines would intersect if they were drawn with complete accuracy. Well, when we solve this equation, we multiply both sides by 9. And we get 20 minus 18y equals 54. I'm not going to go through the details of this again. We'll multiply 9 times this, multiply 9 times this, and 9 times this. Nothing I wouldn't be glad to do. We just don't have time to do it. Okay. We get negative 18y equals 34. So y equals negative 34 over 18, which reduces to negative 17 over 9. Which is approximately 1.9. We can compare that with the 1.5 that we got over there. Okay, and it's pretty close. Now, if we plug, and we don't have time, if we plug this value and this value back into each equation, if I did the arithmetic right, they should come out exactly the same. If we plug in the exact values, now if we plug in decimal round offs, it's not going to be exact. That'll be the fractions, okay? Now, let's see that process even. Okay, well, we obviously get 2 points, but I think almost every problem in the entire assignment, you can easily get 2 points. And so we have 700 and 1600 after 20 and 40 minutes. We're going to put time here. We're going to put our bacteria count or whatever it was here, okay? So the times would be 20 minutes and 40 minutes. So it's real easy then to write down our reasonable scale for the X graph. Make sure that this distance is about the same as this distance, right? Then you have a reasonably scaled graph that you can use for approximations. Okay, then we got 1700 and 1600. Well, 1600 is a portion of that. Because it's easy to repeatedly cut that in half. Cut that in half, we come to about here, and that's 800. Not a good, very good job with that, not too bad. Okay, then cut that in half, and we get 400. And then between 800 and 1600, we can take that interval and cut it in half. We got 1200 there. Okay, well, can we locate 700 on this graph? Well, it's between 400 and 800. So let's go ahead and subdivide this interval in half, and then subdivide each of these in half. And we can see the 700 goes here. So now we can do this. Right, here's our point, 20 minutes, 700, whatever. In 40 minutes, 1600. Now we want to draw an exponential curve. Starts over here somewhere and comes up here and in the shape of an exponential. So the curve might look like this. At this point, we've got a graph that gives us a pretty good idea of whether we're on track when we do the rest of our solutions. Okay, so that's the first thing we wanted to do. We can also look forward to some of the questions. What are the questions here? What's the initial size of the culture? What's the doubling period? What's a population after 120 minutes? And when will the population reach 10,000? Now, we're not going to find 10,000 on this graph. Okay, 10,000 is going to be way up there someplace. And that's not going to do us any good. But we'll be able to solve an equation to get that. Everything else said, what was the initial value? Well, the initial value is the value t equals 0, apparently. They didn't really specify that. They could have. Okay. And it looks to me like y might be about 250. Now, if I do a more meticulous graph, I could do a better estimate. But if I get y equals 900 for my initial value, I know that I screwed up. Because there's no way an exponential function through these points is going to be up at 900 here. The quadratic function might be, but that, that's not going to give us a model of how quadratic function up to give us a model of how that period from. All right, and then ask what's the doubling time? Okay, well, we take any 2 points. Okay, so I'm going to take the point here where we're equal to 800, and the point here where we're equal to 1600, and I'm going to say y double here, and the doubling time is how long it takes that to happen. And I can even say that that looks like a little less than the 20 minutes it takes between 20 and 40. Okay. Is it more than doubles? From 700 to 1600, more than the double. So doubling time is going to be a little less than the 20 minutes it takes to go from 700 to 1600. So the doubling time, I'm going to say, just according to this graph, that would be about 10, about 5, say it's about 17. Just reading that off the graph. Now, that might or might not be a good estimate. It's not a bad one. And the population after 120 minutes, well, we can't extrapolate that far on this graph. You know, we'd have to go out 3 times this far. The graph is going to go way up. And we can't really do a graph on a scale that allows us to do a decent estimate of doubling time and initial value, and also get the 120 minutes or the population of 10,000. So if we get a model that gives us the doubling time close to 17, initial value close to 250, then we can feel pretty good about the model, and we can expect that it'll give us pretty good estimates. The other questions. Okay, so anyhow. Really wanting to focus on the mechanics, okay? But you understand the benefits of drawing a graph, because now that you've got a graph and you've got y equals a e to the kt form of the function, and that's on your standard exponential forms, a equals b to the t is the other, and the a equals 2 to the kt would be okay also. And has its advantages. Talk about that more in the support course. Okay, now our two simultaneous equations, we take x equals 20, y equals 700, and we get 700 equals a e to the 20k, and our second point, y is 1600 and x is 40. So we get this. Now we solve the simultaneous equations. For a and k. So we write it down 700 equals a e to the 20k, 1600 equals a e to the 40k. We solve the first equation. We solve it for one of the variables, and we're probably going to solve it for a, because solving it for k would involve logarithms and stuff. And it's just so easy to solve for a, there's no point in trying to solve for k at this point. We'll have to solve for k in the next phase, but not yet. So a is 700 over e to the 20k. And then we take that and plug it back into the second equation. And we get 1600 equals, well, a is now 700 over 20k. Times, and it's e to the 20k. I tried to do that last time. We did one of these in the support course. And that was going to work at all with the e to the 40k. Okay, so now 1600 equals 700 e to the 40k minus 20k, because we're dividing e to the 40k by e to the 20k. And that's what our rules for exponents and common sense hopefully tell us to do. We get 1600 equals 700 e to the 20k. So that e to the 20k equals 1600 over 700. Well, that's 16 over 7. It's about 1.7, 1.8. Okay. We change this equation to logarithmic form, and we get 20k equals log base e of 16/7, which equals natural log of 16/7. And natural log of 16/7 could be pretty close to 1/2. So we're going to say that's approximately 1/2. It's a little more, a little less. Let's see, it's 16/7 would be pretty close to 1.7. 1.7 is pretty close to the square root of e. I'm going to say it's 0.5. I'm actually a little ahead of myself. Because I can now say that K equals the natural log of 16/7 divided by 20. And at this point, you plug out into your calculator, do it carefully, and you're going to get something like 0.5 over 20. Which is like 0.025. Now, let me check that out against the rule of 72. It's going to have a doubling time of a little less than 30, about 20. Yeah, that's not a great estimate. Well, yeah. Doubling time is clearly less than 20. So something's wrong somewhere in the stuff that I did in my head, but your calculator is going to be more accurate than my head. Okay. So this is not a very good estimate. Still, process is what it is. So our conclusion. Okay, well, wait a minute, I didn't go back and find A. Okay, so I've got to take this value of K and plug it in up here to find A. So I'll do that up here. Remember, A was 700 over e to the 20K, which is just equivalent to the first equation. This equation tells us this. And that's 700 over e to the 20 times 0.025. Which would be 700 over e to the 0.5. Which is 700 over about 1.66 maybe. And conveniently, that's 5/3, so it'd be 3/10, 2100 over 5. Be about about 400. Our conclusion would be then y approximately 400 e 0.025 t. And as I said, when I got this here and had a bad doubling time, I knew that something was haywire. I still don't spot what it was. Because most of the estimates are pretty easy estimates, but I messed something up. I'm not going to go back and try to figure it out. It's going to say, well, okay, at this point, I'm going to go to my calculator. Then I'll look at what I did with my estimates and see where I really went wrong and try to learn something about how to not screw up my estimates. Okay. If I look at the graph, this makes no sense because if t is 0, y should be 400. Okay, well, kind of makes a little bit of sense. Initial values y is about, I estimated y is 250. Okay. And the value I get from doing the algebra and estimating my numbers would be 400 because if t equals 0, this is going to be 400 because e to the 0 is 20. So there's something off, but the process is correct. Again, do it with the calculator. Come out with a good thing. Thing I want to emphasize is simply take your data, boil it down to where you can put 2 points on a graph. If you don't do that, you're not going to get anywhere. Even if you don't draw the graph, if you boil it down to where you put 2 points on a graph, then you know what coordinates to put into the form of the function to get two simultaneous equations. Again, I strongly recommend the graph so you can make estimates. Then you figure out what form you want the function to be. If it's an exponential function, again, it's probably going to be y equals b to the t or y equals ae to the kt, whatever your preference is. One could be easily converted to the other. Okay, you get the two simultaneous equations, you eliminate one of the variables. In this case, it's pretty much always going to be a that you eliminate. So you eliminate a by solving one of the equations for a and plugging that into the second equation. Then you do the arithmetic and you figure out what k is. Since x is in the, or k is in the exponent here, you know you're going to have to use logs at some point. But that should be obvious to you. When you have the equation 20 e to the 20k equals 16/7, then it should be completely obvious that you convert that to logarithmic form. And once you do, it's easy. Why don't you keep your wits about you and don't make a bad estimate like I did. Okay. But you're going to use a calculator. Then you take that value of k and essentially plug it into the first equation or the second, doesn't matter, and see what you get for a, and then you write out your estimate. Then, of course, you have to figure out what your doubling time is. You know, we've done that many times, so I'm not going to take time to do that because you need to move over into solving simultaneous equations. Something you should have done quite a bit of in your prerequisite courses, and somebody probably did, somebody probably didn't. It's been a while since somebody might have had those courses, so we're going to need some time on that. Okay, last thing we do should be easy, but I'm finding it's not as easy as it should be. All right, there's the process. Use it. Okay. And once you have the model, find the initial value, find the doubling time, find the count. When t is 120, you just plug 120 in for t. Find when, I'm sorry. Find the count, I think I should have. Find the count after 120 minutes, plug in 120 for t. Find when the count is going to be 10,000. You plug in 10,000 for y and solve for t. You have to use logarithms, but it's straightforward. Okay. Okay, I'm going to go over just real quickly what we did in the preceding support class. You got two simultaneous equations in x and y. You can understand that that's the equation we could graph. And so is this an equation we can graph? Now, how do we graph it? Well, I'm not going to drag it out of you. I just find the intercepts. How do you find the x-intercept? You let y equal 0. How do you find the y-intercept? You let x equal 0. That should be ingrained. Okay. You should absolutely automatically think that when you see these equations, I can graph these by the intercepts. And here's how I find them. Here's what they mean. Okay. So if y is 0, you're going to get 2x equals 16, so that x is going to equal 8. So you have the point x equals 8, y equals 0. If x equals 0, it's going to give you the y-intercept. If x is 0, you get 8y equals 16, so that y equals 2. So you have the point 0, 2, you have this point and this point, 8, 0, 0, 2, and you draw a straight line. That's really simple. Okay. They should also be able to draw based on the slope and the y-intercept. This only works well if neither of the intercepts is too close to the origin. Okay, if the intercepts are really, one of the intercepts is much smaller than the other, it's going to be difficult to maybe get a good equation. Then if it goes through the origin, you only have one intercept. Okay, so you have to be able to use the slope and the intercept as well. And you can do whatever works for you, but for most equations, the intercepts are going to give you the quickest and probably most accurate graph. Okay, so this equation, let y equals 0, 4x equals 6, x equals 3/2. So you have the point 3/2, 0, which is, I didn't, messed up, didn't have room to label. I can actually label it. So I know where everything's going to be. And there's a point 3/2, 0. And if x is 0, -2y equals 6, so y equals -3, so you have the point 0, -3 here. And there's a straight line. And now we estimate the coordinates to the point where the two lines cross. Because our goal is to find a value of x and a value of y that makes both equations true. We're not going to get, usually not going to get an accurate result from a hand-drawn graph, but it should be accurate enough that we get values that nearly satisfy each equation. Okay, so the values that we estimate were 2.5 and 1.5. X is 2.5, y is 1.5. If x is 2.5, multiply that by 2, we get 3. Y is 1.5, we multiply that by 8, we get 12. Okay, let's say get 3 or something like that. 2 times 2.5 is 5. 1.5 times 8 is 12. 5 and 12 add up to 17, and 17 is pretty close to 16. So that's a pretty good estimate, at least for the first equation. Okay. The point 2.5, 1.5 isn't exactly on the graph in the first equation, but it's close. Now, is it on or close to the graph of the second equation? Well, if x is 2.5, 4x is 6. If y is 1.5, -2y is -3. 6 and -3 add up to I multiplied 4 by 1.5. Let me say it again. X is 2.5, 4x is 10. 2.5 times 4 is 10. If y is 1.5, -2y is -3. 10 minus 3 is 7, and 7 is pretty close to 6. So we know that our solution is going to be kind of close to this. Now it turns out, I find the formula I'm doing, integration. I hope I did. That's what maybe I did. I think. Well, actually, oh, here it is. Okay. Wouldn't hurt my feelings too badly to have to go through it again. Didn't want to go through all that again. This time. I did it all. So we need to move on to this. So we write down the two equations. Okay. Now, having written down the two equations, remember what we did a minute ago when we had the two equations for the exponential graph. We eliminated one of the variables. We solved the first equation for A, and we plugged that into the second equation. So we eliminated A, and we got an equation just for K. All right. Here, we're going to want to eliminate a variable, and we could use the method of substitution. We could like solve this equation for y and then plug that in here for y and get an equation in x and solve for x. Okay. We're not going to do that. It doesn't fit in with what we're trying to do. We're going to use the method of elimination. We observe that if we multiply -2y by 4, it's going to match the 8y, but it's going to be negative, right? Okay. Well, we can't just multiply the 2y by 4 unless we also multiply everything else in the equation by 4. Well, we do that. Okay. Observing that 4 times negative 2y is equal and opposite to 8y, we choose to multiply the second equation by 4. And when we do, well, we get, multiply this by 4 gives us 16x, this times 4 gives us 8y, and 6 times 4 gives us 24. Okay? We write the first equation down again, and we write the second equation in this form. Now, that's going to allow us to add these two equations and eliminate y. Because 8y negative 8y gives us 0. Now we have an equation for x, which we easily solve. Then we can plug that x value into one of the equations and get a y value. Okay. Now that should be very familiar to you, even if it's been a few years since you did it. If you did enough of it, which a lot of times doesn't actually end up happening, you would remember. Okay. If you don't, well, it's not that hard to learn. Plenty of opportunity to learn it. So whether you know it or not, that's the process. Now let's look at really the way we format this, and then we'll do one. Okay. And let me observe first, when we multiplied this equation by 4, that didn't change its graph at all. It didn't change its solutions at all. Because what are the intercepts? If x is 0, we get negative 8y equals 24, so y equals what? Negative 3, right? So you have the point 0, negative 3, which is exactly the point that we used here. The intercept didn't change. The x-intercept didn't change either. If we let y equal 0, we get 16x equals 24. X is 24 over 16, which reduces 3/2. So we get the point 3/2, 0, the same as we got with this equation. Multiplying through the equation by 4 did not change a thing about the equation except the number, the coefficients. It didn't change the solutions. It didn't change the location of the graph. Okay. So that this equation is totally equivalent. Okay. So that when we have these two equations, well, talk about what that means. Okay, now I wrote this down. The way I wrote this down is I wrote a big 1 here with a circle, not that big, but a 1 with a circle around it. Okay. Got 1 with a circle around it, indicating that this is the first equation that we had previously. Okay. Then I do 4 times circle 2, meaning I do 4 times the second equation that I had in the last step. So now I've got 2 equations, system that's totally equivalent to the first system. Graphs are the same, solutions are all the same. Now, logic is, well, this equals this, and this equals this. So if I add this to this, it ought to give me the same thing I get if I add this to this. Okay. These two things are equal. These two things are equal. I could add either of these to either of these, and then add another pair like that, and I'd still have equality. Well, the way I add this, I add this side to this side. When I add these two sides, 2x and 16x makes 18x, doesn't it? And 8y and negative 8y makes 0. So we've got 0. 18x plus 0. And 16 and 24 is 40. So I get 8x equals 40. And if my nose doesn't stop itching, I'm going to go half the screen. Okay. Somebody punch me in the nose hard, please. Anybody want to do that? Probably everybody wants to do that. Forget it. Let's do that. 18x equals 40, right? Okay, and when I add these two, I get this equation, which just comes down to 18x equals 40. So it's easy, x is 40 over 18, which reduces down to 29ths. Okay, now I also wrote that out as 2 and 2/9 mixed number, and that's approximately 2.2. It's 2.2222. Okay, all we need is a 2.2. You don't really care about the 2 and 2/9, just a way to get to 2.2. My estimate here was these lines should cross when x is 2.5. Okay. Well, we got Doing the algebra, we got 2.2 instead of 2.5. Now remember, our estimate 2.5 gave us 17 equals 16 and 7 equals 6, right? Well, the estimate 2.5, 1.5. So my 2.5 really should have been closer to 2.2. And I'm not going to, by estimates, yep, 2.22222 repeating an infinite number of times. I can't get that accurate, okay? So anyway, I get 2.5 where I should have gotten something very much closer to 2.2. Should have, ideally would have, if I'd have had a really, really accurate graph. Okay, there's my X value. Now, how do I get a Y value? Well, I just take the X value and plug it into one of the equations. And this is what I get. I choose to plug it in this equation, which brings me around to this. 4x becomes 4 times 29ths. And I use the accurate value. I don't use decimal values because I'm going to ask for exact solutions. You're not going to get exact solutions by rounding off numbers that have denominator 9. Okay. So we substitute the 29s for this x, we get 4 times 29. So then we got our minus 2y equals 6. So we have an equation. So plugging this into this equation gives us this. How do we solve this? Well, do decimal approximations. You're not going to get the right answer. You might get something close to the right answer. It might even, in an application out there in the real world, be close enough. Probably would be if you don't round off too soon. Okay. In this course, we're doing exact answers. So we multiply both sides by 9 because always when there are denominators in the equation, you multiply by the denominators. People still not doing that, but that's what you do. Pick up on that. I don't know why it takes people so long, and don't feel bad. It always takes people this long to pick up on it, and most people never do. I don't know why, because it simplifies equations so nicely. Okay, so anyhow, you multiply both sides by 9. Now, multiplying 4 times 29 by 9, uh-oh. This is terrible. I really screwed that up in the last class. I didn't multiply by the 4. This should have been 80. Okay. So it should have 80 minus 18y equals 54. And then I shouldn't have gotten a negative result, and I kind of obliterated that. I'm going to get negative 18y equals negative 26. Cool. So y equals 26 over 18, which is 13 over 9, which is approximately 1.44, something like that. Okay, well, I didn't check this. So if I check this using 13/9 for x and 20/9 for y, I get 2 times 13/9, 46/9. I get 160/9. So I get 176 over 9, which isn't 16. I'm sorry, I got 49 there. And 8 times 13 is 104. It's 144 over 9, which is 16. Okay, so it works. Again, I reversed those. But y in the fraction for y. So if I check these fractions up here, everything comes out very nicely. It's not hard to check because I have the same denominator for both of these. And I would get, I can't tell myself I'm going to do it. I get 4 times 20, which is 80/9, minus 26 ninths, which is 54 ninths, and 54 divided by 9 is 6. Okay. So I finally have a good solution. I should have checked my solution before and realized that I made another error there. Okay. What I have isn't right. Now, there are a couple of comments on this board. First of all, it's important that I write down the entire system. Because if I don't have the entire system, the two equations, I can't have this. Okay. And I might try to add something wrong or something like that. I do the whole system. I write it down there. But with the second equation multiplied by 4. Right. And then I know if the new second equation was graph would be the same as it was when I did the original, and I pointed that out already. Those are important points to understand, to really understand what's going on here, rather than just memorize the steps, which you're going to forget fairly quickly, unless you understand what the steps mean. And then you're going to know it more securely. And I know you're probably still going to memorize it long enough to do it in the exam and then forget it. That's not the good way to do it, because this is something that you have to do again and again. If you use mathematics or if you have to do additional mathematics courses. Try to understand what's going on. Try to understand why it's so. Okay, well, let me give you another problem. So let's do okay. There it is. What's the graph? Then solve it algebraically. We'll leave this up here. We can see it. Then after I see that you're doing okay with the graphs, I'll move the board away from the algebraic solution. Okay, so graphing. If y equals 0, then 5x equals 23, so x would be 23/5, which would be like 4 3/5, 4.6. So we would have point 4.60 on the first graph. If x equals 0, 9y equals 23. So y is 23 over 9, which is 2 and 5/9, which is between 2.5 and 2.6. So I'm going to say that's 0 to 2.6. Now I threw a curveball at you, but I used the small number 1 here. Okay. If y is 0, x is 1/7. But where is 1/7? Well, 1/7 is like here. Okay, well, let's say that's 4, 2, 1. Yeah, 1/7 is like here. And if x is 0, y is negative 1/3, which is like here. Okay, so we get. Here's well, that's okay. Kind of ignore this one. So we would have the point 1/7 and the 0.0 -1/3. Those points are both so close to the origin that we're not going to be likely to get a very good graph unless we think about another way of looking at the equation, which would be solve for y. And the intercepts here for the second equation are just too close to the origin. So what we do is we put it in slope intercept form. Slope is 7/3, y-intercept is -1/3. Okay, so we can use the y-intercept and we do a slope of 7/3, meaning we go over 3 and up 7. Your run would be 3, your rise would be 7. So we go over 3. Now 4 is there, 3 is there maybe. And if that's 2.67, might be up about here. So let's just talk a little bit. Let's say that's the point. Yeah, well, based on the slope and everything, you need to review chapter 2 if you don't remember how to do this. Okay, you need to lock that in. You need to lock everything in this course so you can do the next thing. So you want to lock that in. It'll be in the final. It's part of this, it's part of chapter 2. You can expect to see it. So we label these graphs. This is the graph of y equals 5x. 5x plus 9y equals 23. And this is a graph of 7x minus 3y equals 1. And the intersection point here has an x coordinate and a y coordinate. Okay. Now, if this is 4, then this should be 2. That looks like about 1. If this is 2.6, that could be 2. So reasonable estimate. Intersection pretty close to the point 1, 2. Turns out if you plug those in, that's right. Because I decided to be nice to you and give you something to algebraically not have a lot of fractions in when you do the algebraic solution. So if you did a careful enough graph, you might have actually decided to estimate 1, 2. Okay. Now the graph is hard enough to do because these intercepts being way too close to the origin, and you have to use kind of slope intercept form. You might well not have got an estimate of 1, 2. We wouldn't expect that. Okay, well, we're going to solve it algebraically. We observe that if we multiply the second equation by 3, we match up the coefficients of y so that they're equal and opposite. Then when we add them, the y will go away. And so we write down equation one. Now I put a circle around one here to indicate that I'm writing down the first equation that we have in the previous step. So we got 5x plus 9y equals 23. And then for the second equation, I say, well, we do 3 times equation 2. Then I put a little wavy line between this and this so that we don't confuse these numbers with something in the equation, okay? So we multiply this equation by 2, we get 21x minus 9y equals 3. Multiply both sides by 3. Okay, meaning we distribute the multiplication by 3 here, and we just multiply 1 by 3 here. We add these, we get 26x plus 0 equals 26. So that 26x equals 26. And we conclude that x equals 1. We then take this x equals 1 and we plug it into, let's say, the second equation. Could be either. Okay, and that gives us the equation 7 times 1 minus 3y equals 1. Yep. So that negative 3y equals negative 6, so that y equals 2. Solution point would be xy equals 1, 2. And that totally agrees with that was an honest estimate on my part, you know. Couldn't see any reason to make it anything but 1, 2. I could have fudged it so that we wouldn't get an exact solution, but that didn't seem to be a good idea. Okay, so there's the process. Very simple. But you do have to identify what multiple to use. Now, it can be a little more complicated than that. Okay, let's have this system. So we're just going to solve this algebraically. Oh, sorry, I should have that stack of paper closer to you. Didn't want to risk spraining it. Okay. Okay. There we have it. So we're going to do this. I first noticed that there's no convenient number to use to match up either my y's or my x's. Now, since I have a positive and a negative multiple of x, I'm going to pick on x. In order to get the x's to subtract off, be equal and opposite, okay? I have to multiply the first equation by 7, and the second equation by 3. Because if I multiply 3 by 7, I get 21. If I multiply -7 by 3, I get -21. So I get 41x plus 15y. Not 15, 35, one multiply by 7. Okay, equals 98. Multiply 3 by the second equation, I get -21x plus 9y equals -33. Then I add my two equations, and I get 44y equals something that shouldn't be. What's going on? Well, my solution is going to be as nice as I wanted it to be. Get 44y equals 65. So y equals 65 over 44. Okay, well, it's going to be a little messy, but I can bring this up here. And I can plug this into either equation. If my numbers get too big, I'm going to plug it into the equation that has a smaller multiple of y. I plug this into this equation, and I come down here and get -7x plus 3 times 65 over 44 equals -11. Then I multiply everything by 44. And when I multiply this by 44, the 44 multiplies divided by the 44 in the denominator, so I only end up with 3 times 65. Numbers aren't going to get all that horrible, so I do with my head, be careful. So 7 times 4 is 28, 7 times 40 is 280, 280 and 28 is 308. So if I'm lucky and did that multiplication right, I get this, and this is equal to 195, and this is 484, and it's negative. Okay. Then I add 125 and 195 and -484. 200 and -484 gives me -284. That ends up -289. And I get -308x equals -289. And I know this was obvious to you when you first saw the problem. Our solution is x equals -289 over 12. Negative over -289 over 308. Now, did that just pop into your head when you first saw the equations? Well, no, it didn't. Okay. So what we see is this is around 1.5. This is a little less than 1. And something seriously wrong. I must have screwed up something over the equation, but I don't see it. Okay, well that's one way to look at the process. We don't have time to look at this with the matrix, but we'll pick that up next time. I was hoping to anticipate that. Okay, if we check this, I don't think this gets out. I'm sure it doesn't check out. I don't see the problem. Okay, let's do. No, don't see there. I think one more page is everything okay. Okay, well, so be it. So I did intentionally make an error, but I worked kind of fast. So I'll see what it is. By checking, I realized that I made an error. Okay. You're gonna make errors too. Unless you let ChatGPT solve the thing for you. And you don't learn anything by doing that, so don't do that. You're gonna make errors. You wanna don't, you wanna not skip the checking step. You wanna get in the habit of checking. Because of course, on an exam, if you get the wrong result and haven't checked it, you're gonna lose a lot more credit than you're going, if you just made some simple little error, checked it, can't find the error. You go on. I wouldn't penalize that very heavily at all, unless the solution was very important for another part of the problem. Okay. So, for various reasons, especially for your own understanding, check everything. Check these problems when you do. Okay.